Hello, welcome to another module of this course, Analog Circuits. So, in the previous module we had seen what is the effect on the stability for a system whose open loop transfer function has just a single pole, and we had seen that the system will continue to be unconditionally stable, that is the feedback does not affect its stability. Let us now do the same analysis for a system which has more than one poles. Let us first see a system that has two poles in the open loop transfer function. So, such a system will have an open loop transfer function like this, the characteristic equation will be given like this. The characteristic equation of the closed loop system, that is, which is equal to 1 plus a 0 beta upon 1 plus s upon omega p 1 s upon. Now, here I should mention about this beta. This beta is frequency independent. Which means that the beta is not a function of s, okay. It is remains the same for all frequencies. Now, such type of feedback networks are all of course possible. If, for example, if we have a purely resistive feedback network, then beta indeed will be independent of frequency. Now, simplifying this equation further, the C becomes so the C will then become will be formed by equating this equal to 0. Now, from this we can simplify this as okay. The roots of this equation. So, this is my C now. The roots of this equation comes out to what do we see if we plot the roots of the characteristic equation? They are somewhat like this. So, these were my initial roots minus omega p 1 and minus omega p 2. Let me use a fresh page. So, this is my S plane, my initial roots were at minus omega p 1 or and minus omega p 2. Now, from this equation we see, this is the roots of the equation that we have just derived. Now, what do we observe? First thing we observe is that even though the coefficients of the characteristic equation were, or the characteristic polynomial were all real, after solving we see that depending on the value of a0 beta, the roots of the characteristic equation can be complex. Of course, they will be in complex conjugate quantities. If they are complex, then what does it mean? So, let us consider this equation once again a little closely. We see that as the feedback increases till to a certain point, this term within this square root bracket will continue to be greater than 0 till certain value of beta. Then when beta increases further, this term within the square root sign or bracket will become negative, and when this becomes negative, S will become complex. So, S will continue to be real for certain values of beta, then when beta increases further, S will become complex. So, if we plot the root locus or the locus that the roots of the characteristic equation of the closed loop system follows for increasing beta, it will be something like this then. So, to some extent they will converge. Then when the term within the square root bracket becomes 0, from there onwards it will diverge. Okay. So, it will be something like this. However, note that even after feedback, the roots continue to be in the left half of the S plane, and even with increasing, even if beta is increased further, they will continue to follow this vertical line. And so, what does it mean? That it is for a system whose open loop transfer function contains only 2 poles, that system will continue to be stable except when omega tends to infinity. When omega tends to infinity, the roots will converge with the imaginary j omega axis, and thus the system will become oscillatory. Okay. So, it is not unconditionally stable, first thing, is not it? The roots do not enter the right half, or I should say the imaginary axis, until when omega tends to infinity. So, it is not not unconditionally stable like the single pole case. However, for most practical frequencies it does remain stable, because for most practical frequencies the root locus will never cross the j omega axis, neither will it merge with the j omega axis. Okay. So, this is a bit different from the single pole case, where whereas for the single pole case, even for when the frequency approached infinity, the system was unconditionally stable. For the dual pole case, it is unconditionally stable for all practical frequencies except when frequency tends to infinity. Now, what happens when we have more than 2 poles? Let us see the 3 pole case. So, for the 3 pole case also, we can make a similar analysis of the root locus by solving, first writing down the characteristic equation and then solving for the poles, and then seeing how the position of the poles depends on the feedback factor beta. So, for that, a typical case is like this. Suppose initially your poles are like this, I call this minus omega p1, minus omega p2 and minus omega p3. Okay. If suppose we keep on increasing the feedback factor, then the root locus will be something like this. So, again just like the previous case, they start converging. This one, however, will continue to move in the left half, further left. So, it does not pose any problem as far as stability is concerned. However, now with after converging, the 2 poles after converging, they follow a locus which is somewhat like this. So, for certain value of beta, the pole positions might be like this, okay. But then, so these are the new pole position values. So, let me represent the new pole with this green signs, okay. And then for even larger values of beta, the pole positions might be like this. Now, till the time the poles are in the left half of the S plane, the closed loop system will continue to be stable. Once they cross the j omega line and move on to the right half of the S plane, the system will become unstable. So, in other words, there, let me use the black pen, exists a minimum value, or rather I should say a maximum value of beta below which system is stable, above which system is unstable. Two terms which frequently crop up while discussing the stability of a system is what are known as gain margin and phase margin. So, let us see what is gain margin and what is phase margin. Now, while discussing the feedback of a system, recall that we saw that the new denominator, I mentioned that the stability of the system is dependent on the characteristic equation 1 plus A beta equal to 0. So, there are two critical features, one is that when this angle A beta becomes equal to 180 degree or minus 180 degree, then we have a potentially unstable case. The other issue is that not only should it be 180 degree, but the magnitude of A beta should also be less than 1, is not it? Only when the magnitude of A beta is less than 1, even if the phase of A beta is equal to 180 degree, the system will continue to be stable. On the other hand, when A beta magnitude becomes more than 1 at phase equal to 180 degree, we have the system becoming unstable. Hence, these two are the markers or the kind of danger points, that is, when A beta crosses the 1 magnitude value, okay, then we have a potentially unstable case, or when A beta phase is equal to 180 degree, we have a potentially unstable case. Now, here in these plots, if suppose for some value of omega, the magnitude of AB becomes equal to 1, or on a dB scale, that is 20 log AB becomes equal to 0, and I label that frequency as omega 0 dB. Similarly, say for some frequency omega 180, the phase of A beta becomes equal to minus 180 degree or plus 180 degree, both are the same. Then the gain margin refers to the margin available between, or the amount of gain that is available between this omega 0 dB frequency and omega 180 degree. So, this is my gain margin. And phase margin represents the total margin available phase or total amount of phase that is present between this omega 180 and omega 0 dB. So, this is my phase margin. So, if suppose at a particular at omega 1 dB my phase is theta, then I can write theta plus phase margin is equal to 180 degree. In other words, phase margin is equal to 180 minus theta. Now, phase margin for good design should be between 45 degree and 180 degree. Okay. Let us use a sample calculation and see what should be the limit on my magnitude. So, at omega 1 dB, okay, we have AF of j omega is equal to A of j omega upon 1 plus A of j omega beta. Okay. Now, A of j omega is A beta equal to 1 at omega 1 dB. This implies A is simply equal to 1 upon beta. Therefore, this equation becomes 1 upon beta e raised to minus j theta, okay, where theta is the value of the phase at omega. Actually, I should have written this way. Okay. So, where theta is the phase of A beta at omega 1 dB upon 1 plus e raised to minus j theta, right. Now, for phase margin equal to 0, theta should be equal to 180 degree. This implies what? So, if theta is equal to 180 degree, then what does that mean? It means that see when theta equal to 180 degree, my denominator vanishes. So, this implies that AF of j omega will be equal to infinity, which is a clearly an unstable system. Okay. For phase margin equal to 180 degree, theta is equal to 0. Now, these two we are deriving from the formula that we just derived. So, in that case, when theta is equal to 0, your closed loop gain magnitude will be equal to 1 upon 2 beta, which is clearly a stable system. And when your phase margin is equal to 45 degree, theta is equal to 135 degree, and A of f j omega is equal to 1.3 over beta, which is again a stable system. So, in this module we covered the response or the root locus of a system and its potential stability when the open loop transfer function of the system has 2, 3 or more poles. We discussed for 2 and 3 poles, and we saw that when the number of poles of the open loop system is 2, it is stable for all practical frequencies except when the frequency approaches infinite. For 3 poles, for the open loop transfer function of a system having 3 poles, we saw that the system will be stable for certain values of beta, but then when beta crosses a certain threshold value, it will, the poles will move on to the right half of the S plane and the closed loop system will become unstable. Now, even though I did not mention this, but for higher number of poles like 4, 5, 6, we observe similar patterns, that is for certain values of beta the system will be stable, when the beta value crosses a threshold the system will become unstable. And finally, we also studied about what is the gain margin and phase margin, and we saw that for good designs the phase margin should be between 45 degree to 180 degree, and we showed 2 examples where when the phase margin is 0 the system becomes unstable, when the phase margin is 180 degree the system is highly stable. In the next module we will be covering the topics of frequency compensation. Thank you.